Hello, and welcome to Lecture 29 on the consequences of special relativity, specifically length contraction and time dilation. So in other words, we're going to be talking about things getting shorter and time getting stretched out. Now, these are the consequences of special relativity because they follow from Einstein's two postulates of the theory of special relativity, which I talked about in lecture 28. So that definitely lays the groundwork, makes the thought experiment argument about why special relativity must be the case, why we must have things like the relativity of simultaneity because of the universal application of physical laws to all inertial reference frames. Okay, so in other words, physics doesn't just apply some of the time, it applies all of the time. Okay, now since relativity applied to simultaneity between events, that means there must be something weird going on with space, which is length, and time. And that's what we're going to talk about today. Okay, and we're actually going to show the formulas to make those calculations of length contraction and time dilation. So what are our two objectives? All right. So we want to learn how relativity predicts that moving clocks run slow and how experimental evidence confirms this. We also want to learn how, I should say the word learn how the length of an object changes due to the object's motion. So it's a very practical approach of what we're doing here, because really we're looking at the actual problem-solving approach. And with that practical approach to relativity in mind, you can see my first key term is something called the Lorentz factor. What is that? Why should we care? Well, first of all, what is it? Well, it's just a mathematical expression. It is dimensionless, all right? So it's like other dimensionless values you've seen before that are ratios, for example, like the friction coefficient. This one is represented by the Greek letter gamma, lowercase, all right, like that. And what is it? Well, it's this formula right here. Now, I don't typically give formulas in the key terms, but I want to get out of the way that we're defining the Lorentz factor. And it's 1 over the square root of 1 minus this ratio. So it really is practically a ratio of velocity squared over the speed of light squared, where velocity is the reference frame speed. All right, so v is speed of reference frame. Okay, and I really should have a u here. I've used a u everywhere else. So just please consider that, because typically I've been using and trying to be consistent with using the letter u to represent the speed of the reference frame, which in fact you can see in this picture right here, because you can see there u times delta t is the speed of this train, another one of our thought experiments, times the elapsed time. U is the speed of the train, it's the speed of the moving reference frame, s prime, okay? So, but again, why this mathematical expression? Where does this come from? Well, I'm not just going to ask you to memorize it. It comes from in our case, we're going to use an actual geometric argument to show why it makes sense based on the universal application of laws and the speed limit of light. Okay, so we actually will derive this expression. But the reason I'm giving it up front is because it's so important to making calculations of relativity. Almost every time you make a relativity calculation, whether it's length contraction and time dilation like we do in this lecture, or as we will do in lecture 30, when we'll talk about relative kinetic energy and relative motion, we're always going to be using this expression. It's the go-to way to make the calculation, okay? So I wanted to get out of the way because it's so important. And by the way, it becomes larger as v approaches c. So if v is essentially 0, then gamma is approximately 1, okay? But then as v gets closer and closer to c, gamma is going to approach infinity. So if you had something going 99.999999% of the speed of light or something, then your gamma would be very large indeed, okay? Your Lorentz factor. And it essentially tells you how important relativity is going to be in your calculations, which is actually the final example you're going to see in this lecture. But let's carry on with our key terms. Next up is proper time. What is proper time? Well, this is one of those formal definitions that you have to make sure that you can make sense of in your own words and that you can internalize to understand relativity. And I say it's another one because it's similar to when we defined event in lecture 28, where we give a very careful definition to event for what an event is, so we could use that argument to talk about the relativity of simultaneity. Same idea here. What exactly is proper time? All right. Well, proper time is the time between two events at least two events, okay, as measured in the reference frame where the events occur at the same location. All right. So consider this case here. All right. So we'll go back to these two people periodically over the next few minutes in this lecture. We have this woman Mavis sitting in a train that's moving at relativistic speed. This is our imaginary train. And we have Stanley standing at rest relative to the train, watching Mavis go by in her super fast, nearly light speed train. The reference frame of Mavis is S prime. That is the moving reference frame. So moving reference frame. And we'll take Stanley's reference frame as S, and that's the rest reference frame. So rest and moving, okay? And who's measuring the proper time? Well, it depends on what event we're talking about. The events we're talking about is a source of light, okay? That's event number 1. And that source of light is set straight up inside the train. It's going to bounce off a mirror that's attached to the ceiling of the train. Then that light is going to get reflected back down. The reflected light is going to travel back down to the source, which is also a sensor, and the source/sensor sensing the returned reflected light is the second event. So event number 1, emit the light. Event number 2, receive the reflected light. Okay? So where do those two events take, or in which reference frame do those two events take place at the same location? Mavis's, and only Mavis's reference frame. Because for Stanley, the two events of sending the light and receiving the light would take place at different locations. The sending, for example, would take place here, and then the receiving would take place over there. There was movement between them, thus those two events were not at the same location in Stanley's reference frame. Thus, Stanley does not measure the proper time. Only Mavis measures the proper time for this particular series of events, right? If we set up one of these we call this a light clock often, because we can measure the time it takes the light to go back, bounce off the mirror and come back. So if Stanley had set up one of these light clocks in his reference frame, and we were talking about the time for that to happen, well then he'd be measuring the proper time, okay? But the light clock is with Mavis, thus Mavis measures the proper time, okay? It's a very, very important definition there, okay? So what's time dilation then? Well, time dilation states that measured time in any reference frame, such as S prime, other than the one that that measured proper time will be longer. Okay? So if S prime is the reference frame that's measuring proper time because the light clock is with Mavis, then who will measure longer time? Stanley will. The time it takes for the light to be sent up, bounce off the mirror, and come back down will be longer according to Stanley. He will measure the longer time, the dilated time, because dilated means extended or enlarged, all right? Dilated time measured by Stanley because he was not the one measuring the proper time, because of any other measurement other than the proper time, okay? All right, so we'll put that to practice, and we're also going to use Mavis and Stanley and the train in order to actually come up with the Lorentz factor, okay? We'll do that in just a moment. But first, let's define the counterpoint to time dilation, which is proper length and length contraction. And I say the counterpoint because we can arrive at the same result considering space getting shrunk relative to the moving reference frame or time getting extended, right? There are really two ways of thinking about the same phenomenon, okay? Which we'll highlight directly in one of the examples to show you get the same result, either considering one reference frame with length contraction or another reference frame with time dilation. But we're going to go back for now to Mavis sitting in the train. But now her light clock is turned on its side, and it's going to be sending light, reflecting it off a mirror, but horizontally, and it will be going a certain distance with a meter stick set up, all right? And so now we have the proper length, L naught, okay? Oh, and do note that T is the non-proper time, any time other than the proper time. T naught represents the proper time, right? That's just the notation that we're going to use, and I'll label that on the next page, okay? And T, the non-proper time, is always larger than the proper time, okay? All right, but then on to proper length, represented as L naught, so notice the consistency of subscripts, that subscript 0 is always the proper whatever, length or time, okay? All right, so carrying on, we're then going to say that the length of an object measured in a reference frame where other than that, I'm going on length contraction, So let me start over. It's the length of an object measured in a reference frame where that object is at rest, okay? So same thing here. We got Mavis and Stanley. Who's measuring the proper length of this ruler, all right, of that meter stick? Well, it's Mavis, okay? Because the meter stick here is at rest relative to Mavis. It's moving relative to Stanley. So only Mavis measures the proper length of the meter stick. And that one's very easy to wrap your head around. Be like, oh, if you are in the room with the object, then you measure the proper length. If that room has got glass walls and it's moving past someone so someone can see into the room, then they would not measure the proper length, okay? Because the room is moving relative to that person, okay? So that leads to length contraction, and length contraction states that the measured length in any reference frame other than the one that measured the proper length will be shorter, okay? So we see things always get longer and time always stretches out, okay? Relative to the other reference frame. Now motion is relative, right? So, Stanley says, yeah, Mavis is zipping by, but from Mavis's perspective, Stanley is just zipping by the opposite direction, right? It's like he's receding at whatever velocity she's moving at, right? So there's certainly a relativity there that will result in, depending on which reference frame our actual measurement is being made in, because that sets the proper either time or length, okay? But certainly that will be highlighted in the examples to come. But before we get to the examples, we want to present the actual equations of time dilation and length contraction. And in doing so, I also want to do a derivation of them using those same figures with the train, okay? And specifically starting with the proper time relationship to time and the effect that stretching out of time, okay? So first of all, in our key formulas, we've got the speed of light defined to many, many significant figures. And this is useful for certain results where we have particles that are traveling very close to the speed of light. So then we actually might use this. Okay, and I have one example where we have an object, a particle, that's only traveling 1 millimeter per second slower than the speed of light. So certainly this number will be helpful for that. Okay, so the speed of light is about 300 million meters per second. Okay, that's what we often round to if we're using three significant figures. All right, and here we're going to consider again Mavis inside of her very fast moving train, moving reference frame S prime, and we're going to consider the time it takes the light, considering the proper time it takes the light to go from the source, bounce off the mirror, and then come back to the source, okay? So the time it takes, the proper time, okay, the proper elapsed time measured in seconds, okay, delta t naught, is 2d divided by c. Why 2d? Because the light has to go up to the ceiling, bounce back from the ceiling. So that's the 2d, okay? Travel up and then back down. The speed at which light travels is c, thus it's just distance divided by velocity gives us elapsed time, okay? Great, specifically the elapsed proper time. But what about Stanley? What time would he measure, okay? Well, here's Stanley, right, watching. Now for him, the path is not straight up and straight back down, okay? It's angled. Now that angle is usually imperceptible unless Mavis's train is truly moving at an appreciable fraction of the speed of light. But if she was moving, say 80% or 99% the speed of light, then certainly there would be a stretched out triangular path that the light ray would take, all right? Maybe a stream of photons, okay? So in this case, the path that's taken is not 2D, but instead 2L, where L is the hypotenuse of this triangle right there, okay? And we can see that the base of that triangle is half the isosceles triangle, and it's 1/2 u times delta t. Why? Well, why 1/2? Well, because it's half the base of the full isosceles triangle. And why u times delta t? Well, because u is the speed of Mavis's train, right? The relativistic speed, right? And then delta t is the elapsed time in Stanley's reference frame. Okay, all right? So then the elapsed time that Stanley measures must be 2L divided by c. Wonderful. And then we can relate L to D, which we want to do, right? We want to have a geometric relationship between D and L. And indeed we can, because the distance here, this other leg of the right triangle, is still D. So we can simply use the Pythagorean theorem to relate the elapsed time in a different reference frame, other than the one where the proper time is measured, replacing L with just the square root of D squared plus this expression here. Why? Because these are the two sides of the right triangle, right? As we can see in the figure, right? Because D is labeled right there. Okay, excellent. Now we're going to do one other substitution because we want to get rid of D, because D is arbitrary. This derivation of the effect of time changing between the two reference frames should not be dependent on how tall the ceiling is in the train. So we're going to replace D with this expression that has proper time in it. So we'll go ahead and solve this expression for D, and then substitute it into the elapsed time measured by Stanley. Okay? Okay, and we've got our terms. We have everything is squared based on the Pythagorean theorem. We're going to factor out a term here. We're just going to factor out a 2. Oh, actually, never mind. We already had the 2 over c. Okay, never mind. There's no factoring in this step. There will be some other steps. Okay, but what we are going to do is we're just going to simplify it. Okay, now this is great to do for practice, but I'm not going to show it here. Algebraically, we can simplify this expression and relate the elapsed time according to Stanley's reference frame to the proper elapsed time according to Mavis's reference frame. Okay, and we see what we get. Look what we have. We have this measurement elapsed time is the proper time divided by that square root expression. In other words, it's the Lorentz factor times the proper time is the elapsed time. Okay, so we see where that expression comes from, that 1 over the square root of 1 minus u squared over c squared. It really comes from this geometric argument, or at least that's one way to derive it. Okay, all right. So we also want to talk a little bit about proper length and length contraction. All right, first I'll label a couple things here. So u, as I said before, is the velocity of the reference frame, s prime, that's the moving reference frame, that's Mavis's reference frame in this case. The Lorentz factor is gamma, gamma is always greater than 1. Okay. And we can see that delta t, the elapsed time, is always greater than the proper time. And as u increases, so does the value of the elapsed time as measured in the other reference frame. Okay? And u will always be less than c because you can never actually move at the speed of light. Okay? So very important equation. But now on to length contraction. Okay? So looking at length contraction, we have this expression with proper length represented. Well, where does this come from? Because this looks a lot like the original expression we had for proper time, right? Well, it comes from just considering our, our train again, but the horizontal case with the meter stick laid across the seats of the train, right? So there's the proper length. We can see the light beam has to travel from the source, reflect off the mirror, and then go back to the source slash sensor. What distance does it have to cover? The proper length, okay? Because it's not bouncing off the ceiling this time. So we can see then that the proper length is L naught. And the time it takes the light to travel is just 2 times that L naught, because it has to go there and back again, just like when it was bouncing off the ceiling, right? Divided by the speed that the light travels, which is always c. Okay? Excellent, excellent, okay? So notice though that we've turned it horizontal. The reason that we've turned it horizontal and aren't just considering the light bouncing off the ceiling anymore is because we need the length contraction to happen in the same direction as the motion, because there is no length contraction perpendicular to the motion, and the train is moving horizontally, so we need to consider something that's horizontal that will actually be affected relativistically, have its length affected, okay? All right, so there's the expression for the relationship between elapsed time and proper length. Okay, so now we need to do the same thing for the distance that the light travels as measured by Stanley in the other reference frame, okay? So in Stanley's reference frame, the light travels a distance d, which is going to be L plus u times delta t1, okay? Because L is the length that Stanley measures for the meter stick. Notice this is not L prime, this is the measured length according to Stanley, plus the extra distance because the mirror moves as the light is moving, so the light has to catch up with the mirror, right? So the total distance that it moves is the length of the ruler plus that extra distance because the ruler, continued to move ahead as the light was actually traveling along, okay? And again, the idea of the mirror actually gaining ground before the light gets to it would never matter unless the train is indeed moving very quickly, right? U has to be, somewhere close to C, okay? But after the light hits the mirror, it of course gets reflected, so then it travels back. When the light travels back, it's going to travel again some extra distance of U, in this case times delta T2, because we're considering 2 times the time for when the light is incident before it hits the mirror, that's delta T1, and then for the reflected light, which is delta T2, okay? And for both of those expressions, well, starting especially with the one for the incident light, we can just go ahead and solve for delta T1, and if we just divide both sides by C, and we get this expression right here. So this relates the time, the elapsed time as measured by Stanley, to the length measured by Stanley, the speed of light, and the speed of the reference frame, S prime. And then we can do the same thing for the reflected light, okay? So this is just showing that I just algebraically solve for delta T1, all right? That's the incident light. And then for the reflected light, we can make the same argument, but instead of it being going to be plus u times delta T1, it would be minus u delta T1. So we end up with a plus when we solve for delta T2, okay? So we just different signs for the reflected light than for the incident light, right? Because it has to travel it's going to essentially get shortened on the way back. Okay? So then we're going to go ahead and say, well, since the total time is the incident plus the reflected, then delta t is just delta t1 plus delta t2. Okay, excellent. So that's just a matter of then finding a common denominator and simplifying, right? That's all I've done here. I've just literally taken delta t1 plus delta t2, put those two terms together. Obviously, they're very similar terms, right? And then I factored out a c because I want to prepare it for looking like the Lorentz factor. Okay? And the last thing we're going to do is we're going to take advantage of the fact that we're doing this derivation for length contraction second. So we're going to take our result from time dilation. Because for time dilation, we just had to use the triangle, the triangular path that Stanley saw the light take, which I feel is an easier argument to make. That's why I like to do time dilation first and length contraction second. Okay? So we're going to relate this value of the elapsed time according to Stanley to the Lorentz factor and the elapsed time the proper elapsed time. All right? And then we just are going to go ahead and then replace the proper elapsed time with this expression up here, which of course just made sense because this was in the reference frame where the object is at rest, or the meter stick is at rest. And then so when we do that substitution, then we can just go ahead and solve now, because now we have an expression that has L naught in it and L. So it's got the proper length and the length measured in any other reference frame. Okay, so then we just go ahead and solve for L and cancel out the 2 over C. Because we have a 2 over c on this side, right there, and we also have a 2 over c there, so they cancel. Okay, and then we get this nice expression that the length is equal to the proper length times this, all right, and this looks a lot like the Lorentz factor, but it's actually the reciprocal of the Lorentz factor. So then if we write the relationship between length and proper length, we always see that you take the proper length and you divide by the Lorentz factor. And after all, the Lorentz factor is always greater than 1, which means that the measured length in any other reference frame will always be shorter than the proper length. Okay? That's why it's length contraction. Okay, excellent. So there are our two big equations. This one deserves a box as well. I'll go ahead and put a red one around it. But everything else really was derivations based off our figures of our thought experiment of the very fast-moving train. But these are the two big results that we're actually going to apply to some example problem solving. Okay, so let's get on to that. Let's do practice. Now, there are two types of problems here. I think it's totally fair to group them into ones that involve time dilation and then other ones that involve length contraction. Now, I have at least one problem where it involves both, so it's kind of going to be a rainbow color, a little bit of red and blue. Let's take a look at a type 1 problem with example 1. So your starship passes Earth with a relative speed of 0.9998 c. Okay, so 99.98% c. After traveling 10 years in your reference frame, you reach your destination. Who measured the proper time, you or someone back on Earth? Okay. Oh, forgot I labeled these again, the length and the reference frame, the proper length. So now back to the example. Okay, so you measure the proper time. Okay, you measure the proper time because you measure time, right? You use some technique like a light clock or some atomic clock or something to have events all take place in the same location in that reference frame. So that was the way you measured time. Thus, the proper time was measured in your reference frame. Okay, so then if we want to find the elapsed time on Earth, we put in the proper time measured in the ship and just go ahead and divide by the Lorentz factor. Okay, so when we do that, we take the proper time of 10 years. All right, and then we'll just go ahead and then divide by the Lorentz factor, or rather multiply by the Lorentz factor. Sorry, I said divide, because of course the relationship between other time and proper time is that delta t equals gamma times delta t naught. I was just thinking divide because we're dividing by the square root, but of course the Lorentz factor is 1 over the square root. So dividing by the square root is the same thing as multiplying by the Lorentz factor. Okay, so that's what we're doing here. We're multiplying by the Lorentz factor, taking the proper time, multiplying by it, right? And the reason that we're going to get something bigger is because the reciprocal is less, or rather the denominator is less than 1. Notice, since we were given the velocity as a fraction of c, when we plug it in for u, it's real nice because the c's just cancel out right away. So whenever you're given a velocity like this, you can essentially just take the number and just plug it in here and square it because the c squared is canceled. Okay, so we have 10 years divided by this difference inside the square root in the denominator. And when we actually do that, we get about 500 years if we round to 3 significant figures. All right, so wow, so a lot more time passes on Earth because of course this starship is moving incredibly fast. Okay, almost unbelievably fast. It would take a truly unbelievable amount of energy to get any appreciable amount of matter up to that speed, but we'll talk about that more in lecture 30. But point being is that we have huge amount of time dilation, all right? So only 10 years would pass for the very fast moving person. Back on Earth, 500 years would pass. Many generations would go by. Okay, but velocity is relative, right? So isn't it from the perspective of the person in the ship that the Earth is receding at that speed? Let's see. So it may seem like the previous example presents a paradox, since when we consider a light clock on Earth that measures 10 years of time, okay? What happens then, right? We could also consider, measurements made on Earth, okay? So in that case, in the case of the clock on Earth measuring 10 years, well, what is the proper time? Well, in this case, Earth measures the proper time, since the light clock events all occur at the same location in Earth's reference frame. They would not all occur at the same location in the ship's reference frame, so the ship would no longer be measuring proper time. Okay? So in that case, we would just want to use the same expression, except now the elapsed time would be the elapsed time in the ship. The proper time would be the 10 years measured on Earth. When we go ahead and plug in, I'll zoom in on this a little bit. I'm just going to plug in for the velocity of the reference frame, being the velocity of Earth, which is effectively receding at negative, you can see here, negative 0.9998 c. Again, cancel out the c's. When we square, the negative has no effect on the actual calculation, so we get 500 years. So wait, who has extra time pass? Is it the person moving in the starship at high speed, or is it the person at rest that never picked up any high speed? Because it seems like we're getting a contradiction, because we can't have 500 years pass for one reference frame and only 10 for the other, and then also have the reverse happen simultaneously. That would be a contradiction. Okay, so let's see. Since this does seem like a paradox or a contradiction, we can partially resolve the paradox by considering a 2-hour round trip of a ship traveling at relative speed. I'll talk about why this is a bit of a partial resolution in just a moment. The ship is counting increments of 6 minutes and sending a light flash each time. So we're not considering 10 years this time. We'll consider a shorter amount of time in order to make our argument here. All right, so in the figure below, what is the Lorentz factor of the ship on both the outgoing and return trip? And what you want to pay attention to is that the ship is going to send a flash every 6 minutes in its reference frame. Back on Earth, a flash is going to be measured every 12 minutes. Why? Well, because we can see there's essentially a Doppler effect going on, where the ship is moving further away, and so the waves are further spaced as the ship moves away, right? Because it's essentially catching up with the light partially each time it emits it. And if we look at the difference between the elapsed time between each flash sent and each flash received, it's a difference of 2, isn't it? Right? So since delta t equals gamma times delta t naught, right? That's the expression for time dilation. And here the 12 minutes in Earth's reference frame, 6 minutes in the reference frame of the clock, or of the clock, right? Then we get a gamma of 2. Okay? And here I am actually assuming that Earth is the reference frame and the proper time is being measured by the ship. Is that right? Well, it is, because the ship is measuring proper time, and that's and question D here. In this figure below, who is measuring the proper time, the ship or Earth? Because they're the one creating the light pulses. And the light pulses, being the subsequent events, they all occur in the ship, so they all occur at the same location. Thus, that would be the proper time. Okay? Now, we could consider it the other way. We could consider light flashes being generated on Earth. So if we consider a clock on Earth counting out increments of 6 minutes and sending a flash of light each time. In this case, who's measuring the proper time? Well, this time Earth is measuring the proper time, since each light pulse event occurs at the same location relative to Earth. Okay? But let's see, right? Are we going to get the same result here that, according to Earth, extra time passes for the ship, according to the ship, extra time passes for Earth? Are we still going to get that paradox, that contradiction? No. And the reason is because we have a round trip here. We have the ship turn around at this point. So notice that when the ship has turned around and it's already on its way back, sending flashes every 6 minutes, at that point, for a while, all of the further spaced flashes are still going to be arriving on the planet. See? Right? So even though the ship has already turned around, the planet is still receiving the flashes that are 12 minutes apart. Now, eventually, the flashes will start being received on Earth in shorter increments of only every 3 minutes, while the ship then still generates them at a steady rate of 6, but not at first, okay? Not during this immediate after the turnaround, okay? So let's then consider what's going on here. So finally, we can combine the information from considering the time dilation as measured when considering the proper time in both the reference frame of the ship and Earth. So based on counting flashes, how much time did the 2-hour round trip take as measured by the ship and as measured by Earth? And in this case, we'll just go ahead and consider this case above with the round trip, shown in these three figures A, B, and C. All right, so let me zoom out a bit so we can see it all together. So for the ship sending pulses, for the Earth frame, all right, we have 10 flashes at 12 minutes, all right, and then we have 10 flashes at 3 minutes, right? So of the 20 flashes that were sent by the ship, okay, 10 of them were sent, they were all sent at 6-minute increments apart as measured by the ship. 10 of them were received at Earth with 12-minute increments. 10 of them were received by Earth with 3-minute increments. When you sum up all those minutes, you get 150 minutes. On the other hand, in the ship's reference frame, where there's just 20 flashes and they're all 6 minutes apart, so there's only 120 minutes. So we see that by the time the ship gets back, there is no paradox. Which one actually has more time pass? Earth, okay? And the reason is because of the fundamental asymmetry that one reference frame was there was only one reference frame for Earth, but the ship had two because the ship turned around, and the turning around reconciles the paradox. Okay, it does because there's no paradox anymore. We see who has more time pass, and it's the reference frame that just remained at rest and never turned around. Because turning around is acceleration, and acceleration really is the story. But this is the argument that makes it at least seem believable and hopefully clears up that paradox in your minds as you learn the subject. But I do want to briefly mention the idea of acceleration because this doesn't at all address the idea of a one-way trip. Because if we took a one-way trip and arrived, then we could send a signal back. That signal would travel at the speed of light, and there would have to either the signal gets back to Earth, and the people on Earth say, "Hey, we're 500 years older," or the signal gets back to the Earth, and they find out that the people in the ship are 500 years older. It can't be both, right? So how do you reconcile the paradox on the one-way trip? Well, a similar explanation for the one-way trip, as in example 1, requires a consideration of the acceleration initially to speed up to that high speed and then to slow back down when you get there. So there still is acceleration, even if there isn't a turnaround acceleration, okay? Even if there's only effectively one inertial reference frame during the most of the period of the journey, there's still that initial speed up and slow down. And because whenever there's acceleration, then you have to employ the general theory of relativity, which applies to non-inertial reference frames, in order to get that paradox resolved, okay? But we will not cover general relativity, so we can only say that it's something out there for further exploration. But let's get back to numerical examples. With example 2, an example that involves length contraction. Particle accelerators used in physics research are sometimes built in straight lines. You might typically think of them as circular, maybe that's often the case, but there are some straight ones as well. One such imaginary accelerator built in the flatlands of Utah has a length of 12 kilometers. It's a really long straight line, according to measurements made by scientists, okay? The ones that work near this long tube. A neutrino particle is tracked through the accelerator moving from one end to the other at a speed 1 millimeter per second less than c. This is a very, very fast neutrino. How long is the accelerator in the reference frame of the neutrino? Okay, so we first want to establish that the proper length is the 12 kilometers because the tube, the particle accelerator, is at rest relative to Earth and Utah, thus they're measuring the proper length. So then we can go ahead and find the length as measured by the neutrino in the moving reference frame, and it would just be the proper length times this expression here, all right? In other words, dividing by the Lorentz factor or multiplying by that square root. Plug in our values. Here, we weren't given anything as a fraction of c, so we have to plug in all the numbers. Notice the 1 millimeter only shows up in that last digit, okay? Make sure to square the velocity of the neutrino, because essentially that's the velocity of the moving reference frame, and then make sure to square the speed of light, okay? Plug in the expression there in meters, so we get our answer in meters, and we find that we actually get a fraction of a meter. We find that there's extreme length contraction, because there is, after all, extreme velocity, and according to the neutrino, that 12-kilometer long tube is only 3.1 centimeters long. Wow, interesting. That's going to have some big consequences. That means that very fast-moving small particles like neutrinos see a very scrunched down universe. What does that mean for them? Well, we'll talk about that a little bit when we talk about the decay of muons in Earth's atmosphere in an example that will be coming shortly. But first, example 3, which is a real simple idea, almost more of a concept. Two events occur. They occur 100 meters apart, okay? And there's an intervening time interval between them of 0.37 microseconds, Okay, so you got like event 1 over here, you got event 1 or event 2 over here. The distance between them is those 100 meters, and one occurs, and then a delay, and then the other occurs. Okay, so but you want to send a ship between those 2 points. You want to have some super fast ship going along that's going to have it. So we measure the proper time between the events. Well, in order to measure the proper time between the events, the 2 events have to occur at the same location in a reference frame, which means that the ship would have to catch up or would have to arrive at the second event by the time it happens. All right, so the 2 events must occur at the same location in the reference frame with the proper time. So the ship must keep up. All right, so in other words, it has to travel those 100 meters in that elapsed time. So that tells you then that the velocity of the reference frame, or the ship, in order to have proper time measured between these 2 events, is 2.7 times 10 to the 8 meters per second, which is pretty fast, right? After all, it's just 0.3 times 10 to the 8 meters per second less than c. Okay? All right, so now on to another example, example 4. In this case, we're going to consider something much slower than either this ship or the neutrino. We're going to consider a student riding a bus. The bus is traveling fast for buses at 35 meters per second. If the student measures the time of the ride as 1 hour, okay, then how much longer will another student at rest measure the same ride? So how important, in other words, is ideas like time dilation for everyday things like riding the bus, right? So you got one student that's staying in the library to study, another student riding a bus. When they text each other, how off is their perception of time? Well, to do this, we're actually going to need to consider an approximation, because otherwise it becomes almost impossible to calculate. And let me elaborate on what I mean. Okay, so we should expect special relativity to have a very small effect on something with this low velocity. Okay, so let's see what's going on then, right? So proper time is measured in the bus, okay, because the student measured the time. They measured the 1 hours, okay, 1 hour. So we'll use our relationship between elapsed time and proper time with our Lorentz factor gamma. But here, almost any calculator is going to give you the following result. It's just going to tell you these 2 values are equal. Because when you actually plug in the 35, what's going to happen is it's just going to give you a gamma of 1. Because think about it, this is gamma, right? Now here I've written it, instead of 1 over the square root, I've written the power as to the negative 1/2 power. So that's just the same as writing. If I have this is just saying x to the negative 1/2, just a different way of writing it, okay? But when I plug that in, when I plug in v equals 35, this number here is so small that it basically won't affect the calculator to 20, 25 significant figures. And so it's just not going to show up. And therefore, almost any calculator will just show you that there is no effect, okay? So that's a bit of a problem. You can either try a more accurate calculator, one that say has 30 significant figures, or you can use an approximation. So we're going to use something called the binomial expansion, because it allows you to rewrite this particular parenthetical power expression like this, right? It's an approximation, but it's pretty good when we have these kind of cases, slow things that we're looking at the effects of relativity. So that will allow us to estimate the time difference as, here, delta t, but lowercase delta, because we already have delta t's. Because here I'm calling delta t, that's the difference between the elapsed times, as the elapsed time is measured by the student at rest, minus the elapsed time measured by the proper student, okay? Or by the proper student, the proper time measured by the student, where time was measured. Okay, so then we're just going to go ahead and rewrite the delta t as gamma delta t naught, which then will allow us to factor out the delta t naught. And then that means that we just factored out, we just have a gamma minus 1, all right? Once we factored it out, and then we can just rewrite that expression like this, all right? And then actually at this point, I've rewritten gamma with the binomial expansion. Okay, see what I've done there. Now I'm going to go ahead and distribute in the delta t naught, which cancels out, and then we're left with this nice approximation, because it is still approximation, that the difference between the elapsed time is just 1/2 v squared over c squared. And the whole advantage of doing this is just calculator practicality, because you can put this in your calculator and it will give you that small value. Because now you're not going to be rounding something to 1. You're actually going to be, this is going to be relative to 0. So it will tell you how small that value is. All right. So here we can actually plug in our numbers. So the difference between the elapsed times is 1/2 35 meters per second squared divided by the speed of light squared, or 300 millimeters per second squared. And there we go. We get 6.8 times 10 to the negative 15 seconds. Okay. So some amount of femtoseconds, right? A tiny, tiny amount of time. Too small to ever measure in any practical case, right? There's no accurate measurement that actually would show that difference in time, at least not with current technology, okay? And I also ask in part B, what is the distance traveled by the bus as measured in the reference frame of both students? Okay, well, the student at rest would measure the distance covered as just v times the elapsed time plus that extra time, which means that the student on the bus would measure a distance that is shorter by delta d, which is just v times delta t, or the 35 meters per second times that tiny amount of extra time, which means that the distance, the shortened distance around the student would be some 2.4 times 10 to the negative 13 meters shorter. So they would see a compressing of the world around them by this much. But would you actually notice the world getting compressed by that much? No, of course not, because this is much smaller than an atom, right? Because you think about atomic radius, that's on the order of 10 to the negative 10 meters, and this is 1,000 times smaller than that. So this is way too small to measure. Okay? So indeed, special relativity does not apply to everyday velocities like 35 meters per second. Okay, so let's move on to another example. Okay, so here we're going to have an effect that actually is significant. But what we're going to highlight in this example is how the effect of length contraction only applies to lengths that are parallel to the velocity of the reference frame. Lengths that are perpendicular to the velocity of the reference frame don't get contracted. I mentioned this in the thought experiment with Mavis and the train and why we turned our light clock on its side and had it line up with the meter stick, because I said that the bouncing back and forth had to be of the light, had to be parallel to the motion of the train. Well, now we're going to see the other side of that, because we're going to see how the shape of objects changes as the one axis gets contracted. So an observer at rest sees a transparent spaceship fly past them at 98.7% the speed of light. All right, a ramp inside the spaceship connects the first and second floor and is built with a gentle angle of 5 degrees above the horizontal. What angle does the ramp make with the horizontal as measured by the observer at rest? Assume that the motion of the ship is parallel to the floors. Okay, so what we're going to find is we're going to find initially there's some gentle angle. As only one axis is contracted, this x-axis, we're then going to find that the angle gets steeper because essentially the shape changes. It's only contracted along the x-axis because the x-axis is the axis where the velocity is. Okay, so the proper length is measured inside the spaceship. So then we're going to relate the length along the x-axis to the proper length along the x-axis by dividing by the Lorentz factor. And the Lorentz factor in this case, for this particular velocity, is just equal to 6.22, right? Again, dimensionless. And so then we can go ahead and look at our triangle with the proper lengths, okay? So we are just going to say, by using tangent as opposite over adjacent, that tangent of theta naught, so this should be the proper angle, because it's the original angle, is just the length along the y-axis, these are the opposite side, divided by the length along the x-axis. And actually I misspoke, because this is the angle after contraction, which is why we're already dividing by gamma, okay? So this is in fact this angle there. It is not a typo, I just misspoke, okay? So then we can replace both these expressions for the length along the y-axis and the length along the x-axis with the appropriate sides of the right triangle, okay? And these involve the proper angles, because it's the initial values, because here we're going to take gamma into account. And check out what happens. The total length cancels, which is good because it was not given in the problem. And then we can just relate the length after contraction or the angle after contraction to the angle before contraction and the Lorentz factor. So now we have actually a very nice relationship. We've almost derived another equation for this effect of changing angles due to length contraction. So then go ahead and solve for the new angle. And we'll take tangent inverse of tangent of 5 degrees, the initial angle, right, due to the uncontracted length, and then divide by the gamma factor of 6.22, and what do we get? 80.6 degrees. Wow, a lot of effect. But of course, we are going very fast, so this figure is not to scale, right? Because in fact, it would get shortened quite a bit more, and the ladder would be mostly vertical at that point instead of being gently sloping. But of course, that's just how it would be in the reference frame of someone at rest. According to people inside the ship, it'd still be a gentle slope. Okay. Okay. So on to example 6. I think this one is particularly important for seeing how we can approach the same problem either through time dilation or through length contraction. So muons, right, they're real particles. They are in fact created in the upper atmosphere due to X-ray interactions. and they're created at a height of about 10 kilometers above Earth. They travel at a speed of about 98% the speed of light, or 0.98 c, and the muons have a rest half-life of 1.56 times 10 to the negative 6 seconds. That's not the S for seconds there, okay? So that's their half-life because they're unstable, they're going to decay, right? So every muon has a 50-50 chance of decaying after 1.56 microseconds, okay? And so then we're going to use half-life decay rates to compare between the initial population of muons to the current population of muons, depending on how many of those half-lives have passed, by just raising the power of 2 to the exponent of negative of the number of half-lives. So P will be our initial population of muons, which we're going to take as 1 million, all right? Then we're going to consider, that's P naught, all right? That should be a subscript there. That is in fact a little typo. That should say P naught, okay? P is the final population. N1/2 is just the number of elapsed half-lives, right? So the number of times that 1.56 microseconds has actually occurred, okay? And then, so how many muons are left without considering relativity? Okay, so if we just naively ignore relativity, which we shouldn't, the velocity is that great, but if we do, how many muons would we expect to actually survive when they get down to Earth's surface, coming from that upper atmosphere? So we'll start with initial population of 1 million, or 10 million, excuse me. 1 million muons. Okay, so not considering relativity, the travel time would just be the 10 kilometers divided by the speed of the muons, which is 98% the speed of light. And so that means the travel time would be 34 microseconds, okay? And so then if we go ahead and find out how many half-lives would occur in 34 microseconds, we just take the 34 microseconds and divide by the 1.56 microseconds, which gives us 21.8 half-lives. Well, 21.8 half-lives is actually a lot of half-lives. If you, in terms of like radioactive decay, your sample would be, trace amounts after that, because you divide it by half 28 times, right? Or almost 22 times, all right? So if we actually find out the fraction of the population remaining, right? So we just take the initial population, multiply it by 2 raised to the power of negative 21.8, all right? So we take that 1 million, multiply it by this large number, right? Well, actually this very small number, and we only get 0.3. So effectively, no muons. So that means that for every million muons that enter the upper atmosphere, none of them on average will make it to the surface. But that's not what we measure. Scientists can easily measure lots of muons making it to the surface. And even based on the number that are created, and obviously more than 10 million are created, but they get way more than this value would suggest. Why is that? That's because we didn't consider relativity. So what effect does relativity have on the amount of muons that actually make it to Earth's surface? Well, let's think about the Lorentz factor. Good starting point, isn't it? Okay, so the Lorentz factor, of course, is just gamma equals 1 over the square root of 1 minus v squared over c squared. In this case, since we're given v as a fraction of c, we can just take that fraction and square it, and we get a Lorentz factor of 5.03. Therefore, we can then consider the length of the atmosphere in the muon's reference frame. All right, so you can see here in part B, we're gonna consider this in the frame of the muon. Okay, in the frame of the muon. So in the reference frame of the muon, the Earth's atmosphere around it should be contracted. It should appear shorter, shouldn't it? Okay. So then we'll consider the contraction. So the distance of the atmosphere, according to the muon, would be the 12 kilometers, which is the proper length of the atmosphere. Why? Because the 12 kilometers is measured by scientists on Earth, and to them, the atmosphere is at rest, right? So they're measuring the proper length, divided by the Lorentz factor. So we see then that from the muon's reference frame, the atmosphere is only 2 kilometers thick. Well, that makes a big difference, because then we consider that the travel time of the muon in its own reference frame, it's only traveling 2 kilometers. Really, it's not seeming to, it actually is only traveling 2 kilometers. It's still going to decay at the same rate, but it's only traveling 2 kilometers, right? So we just take the 2 kilometers, divide it by its speed, and we find out that the time it takes it to travel that distance is only 6.8 microseconds, not 34 microseconds, okay? So then if we take that 6.8 microseconds and divide by the length of each half-life, 1.56 microseconds, we find out that only 4.36 half-lives elapse according to the reference frame of the muon. Therefore, the population is about 49,000 muons, because we have our 2 raised to a much lower power, which means that a much larger fraction of our initial population will survive, okay? And that's more consistent with the number of muons that are actually measured by scientists. but we don't need to just use the muon's reference frame. There's nothing special about the muon's reference frame. There are no special reference frames. Therefore, we should be able to, and we can, use the reference frame of Earth. In that case, though, we want to consider time dilation, not length contraction. All right? So in Earth's frame, time dilation means that the muon's half-life is slower for us. Okay? Because, right, in our reference frame, essentially the moving object is aging more slowly, and the muon is the moving object, right? So we'll consider the length of a half-life in the muon's reference frame, and it's just going to be gamma multiplied by the length of the half-life in the rest reference frame. So it's just the Lorentz factor. I'm zooming in on this a bit because it's smaller. The Lorentz factor multiplied by the rest half-life, and we find out that according to Earth-based scientists, muons don't have a half-life of 1.56 microseconds. They have a half-life of 7.8 microseconds. Well, again, that's going to make a big effect, because when we take the travel time according to Earth, which is 34 microseconds, because it's the longer travel time, right, as we saw in part A, well, if you take that 34 microseconds and divide by the 7.8 microseconds, the dilated time, then we find out that, yep, no surprise, only 4.36 half-lives have elapsed. So then, according to the Earth's reference frame, we still get a population of 49,000, consistent with actual observations. Okay? So pretty neat. We can go at it two ways, considering either reference frame, using length contraction in one case, time dilation in the other. Okay? Well, let's take a look at our final example. Example 7. Okay? We're going to start with a satellite, which is a throwback to previous material and formulas you probably haven't seen for a while, but we'll quickly move through that part, and then we'll talk about how relativity is affecting a satellite, because satellites move fast, right? So for a satellite in low Earth orbit at an altitude of about 450 kilometers, which is considered low Earth orbit, above the surface, what is the percent error between the measurement of 24 hours measured on the satellite compared to 24 hours measured on rest at Earth? And this might matter, right? Because if we have significantly different times measured for clocks on satellites, and we're using satellites for sophisticated calculations, then we have to account for that, right? Well, first we're going to use Newton's laws to find the velocity of the satellite. And that's simply a matter of balancing the centripetal force with the universal gravitational force. And so then that's the effect. We find that the velocity of the satellite is equal to the square root of the gravitational constant times the mass of Earth divided by the distance of the satellite from the center of Earth. Notice that this velocity is independent of the mass of the satellite, as it should be. Plug in our particular values, including the gravitational constant, the mass of the Earth, and the radius of the Earth plus the altitude of the satellite, which gives us our overall distance. And we find out that in order to maintain a stable circular orbit, our satellite is moving at 7,640 meters per second. And again, this is something that you would have seen in a mechanics course on physics. But we're done with that, and we can go ahead and use this velocity for the satellite and see what relativistic effect this speed has. Now, we should notice right away that this is certainly faster than the bus at 35 meters per second, but it's rather slow compared to our other relativistic speeds. So maybe we shouldn't expect too much relativity here, okay? So we'll go ahead and find the gamma factor in this case, all right, the Lorentz factor. And we find out that it's not quite 1, but it's pretty close. We have to go out to like the 12th significant figure to get the actual effects of it, okay? So it would show up on a calculator, but just barely, all right? So then we can go ahead and consider the percent error. So this is the time measured in the rest reference frame. This is the time measured in the satellite reference frame. And we're just going to consider the difference between those times, divide by the proper time to get a percent error. Okay? So then we'll go ahead and replace the elapsed time measured in the reference frame that doesn't measure the proper time with a gamma T naught, right? Just from one of our basic equations. And we see that right away then all the proper times cancel out. So it doesn't actually matter how much time was measured, whether it was 24 hours or 24 seconds. The fact is it's just going to depend on the gamma factor, right? So that means that the percent error is actually just going to be gamma minus 1 times 100, all right? And it's independent of the actual duration of time, as I said. So in this case, if we plug in our really, really small gamma factor, then we find out that our percent error is just 3.24 times 10 to the negative 8%, right? So we've got a 10 millionth of a percent error. Not much. So I guess we're fine not worrying about special relativity as it applies to satellites, all right? Unless you're literally making measurements with that many significant figures. But that does beg the question, how fast must an object move for time dilation to result in a 10% error, a significant error, right? Well, how fast do we have to be going? Well, certainly a lot faster than 7,640 meters per second. Let's see how fast. Is it fast as the fastest space probes that are moving maybe 25 25,000 meters, or 25 instead of 7,640 meters per second. There are some space probes that are moving 25,000 meters per second, or even 40,000 meters per second. Is that enough? No, probably not, because it's not all that much faster, especially considered or compared to the speed of light at 300 million, right? Let's see. Okay, so we're simply going to find that velocity, all right, such that this percent error, which is just gamma minus 1 times 100, is equal to 10. All right, so then it's simply a matter of then replacing this expression with the actual expression involving gamma. And all I've done here is just divide both sides by 100 and subtract 1 by both, or add 1 to both sides, which is why we have 1.1 over here. Okay, so then I'm just going to clean this up a little bit. All right, take the reciprocal, square both sides, all right, which is where the 121 comes from. All right, and then I'm just working here to isolate v. All right, so when I finally do, I find that the necessary velocity in order to get a 10% error between the two measured elapsed times is just going to be the square root of 21 over 121 times the speed of light, which in other words is 0.417 c, or 41.7% of the speed of light, which works out to be 1.28 times 10 to the 8 meters per second. So you have to be going very fast indeed to get significant errors between your elapsed time and your proper time. Okay, and that's why special relativity wasn't immediately evident to ancient scientists, because nothing moved that fast that they could measure. Okay, all right, well, I hope this lecture on relativity has been both interesting and informative. We have one more lecture on relativity left with lecture 30. Thank you so much for watching.